To make a polymer, we usually need monomers or small repeating units. So you have tiny molecules that you can link them up and chain them up in order to make a macromolecule or a polymer. Now, before we can talk about condensation polymerization, let's just review what addition polymerization is, then we get into condensation. For addition polymerization, you should remember that you need a carbon-carbon double bond, and then you do not form byproduct, it's just a link of chains. For example, if I take tetrafluoroethene, and if you put N, which is a number bigger than 10,000 or 40,000, in order to make a meaningful polymer, you are going to end up with a link of carbon chains that are saturated or single bonds. So I'm just showing one segment, but the double bond becomes single bond, and we put the N as subscript, and this is a polymer known as Teflon commercially. Now, condensation polymerization, the monomer, rather than a carbon-carbon double bond, needs to have at least two functional groups, reactive functional groups. And you usually have a byproduct. You condense or lose out H2O or HCl. Some example, for example, it could be something that has hydroxyl on both sides. So if I give you ethene diol, it looks like this, has two OH groups on both sides. So this is one example of that. Ethane 1,2-ethane diol. Di stands for 2 and ol is your hydroxyl group. So this is a monomer that we can use for condensation because it has two functional groups. We could have carboxylic acid on both sides of a molecule. For example, if I give you a benzene ring sandwiched between two carboxylic group, is also another example of a monomer that we can do condensation. And this is carbon 1, 2, 3, 4. So this is 1,4-benzene. Since you have two carboxylic, we call it dioic or dicarboxylic acid. So this is another example of a monomer that can be used for condensation. You could also have something that has different functional groups on both sides. So for example, I can give you an amino acid. On one side you could have carboxylic acid, and on the other side you could have amine group. So this is also a possible monomer that you can make it into polymer condensation, and that's protein because amino acids link up to do that. Now let's look at two examples that you need to know. I want to get into polyester, but let's just talk about esters one more time. You should remember esters are a combination of alcohol plus carboxylic acid. A simple one, so we can have methanol, C2H5OH, plus ethanoic acid. And I put the functional groups next to each other so they have a proper orientation to react. The OH of the acid and the H of the alcohol will condense out, and that's the tiny molecule or the byproduct you lose. And then the remainder of the molecules come together and they link up to have an ester linkage. So in this case you make an ester which is ethyl ethanoate. Now this is not a polymer, this is just the ester. How do we make it into polyester? So let's just have alcohol that has two functional groups. So I'll put the 1,2-ethane diol back. Well, let me correct this and put OH rather than that. And let's have n molecules of this, so n is just simply a large number, and let's just put a molecule that has acidic side on both sides. So I give you 1,4-benzene dioic acid again, and now they're going to link up, except you will have a long chain. So I'm going to write one segment down here. The oxygen is here, C2H5. Now remember that the hydrogen of this alcohol and the hydroxide of the acid, they will condense out. So I'll continue with the remainder without the H2O that is being condensed out. And now you will have a polyester. So now this is, since we have n molecules of each, is n plus 2n minus 1 H2O. And you can sort of reflect and decide why is this 2n minus 1. But you should realize it, and then you should remember after that. So this is example of a polyester that we have formed, and it has a commercial name. The trade name for this is rather Dacron. So this is just a trade name by DuPont. Now let's look at another version of condensation polymerization when there is amide linkage being produced. Now you should remember what amides were. They were simply, instead of alcohol, this time you have amines plus carboxylic acids, and you form a linkage known as amide, or in biology you call it peptide. So if I give you a methylamine, let's put it next to methanoic acid, there will be a condensation. Then again, between hydroxyl of the acid and the H of amine, they come out, and the remainder of the molecule looks like CH3N hydrogen, C double bond O, H plus loss of H2O. Now this segment here is a new functional group being formed, and that's your amide linkage. Now how do I make a polyamide? Just have monomers that have the two functional groups. So for example, I can give you 1,6-diaminohexane, which looks like NH, and then you have CH2 6 times because it's hexane, and NH2 on both sides. Plus, now let's just have a carboxylic acid. For example, we can have hexane 1,6-dioic acid. Hexane 1,6-dioic acid. Now this molecule is with 2 carboxylic acid, but the carbons are part of the numbering. So you would have 4 CH2 sandwiched between the 2 carboxylic group. And then let's just condense it out. The H and the OH come out. And I'm going to give you one segment of this polyamide that we formed. So it's N, H, and I put the other H outside. This time I show it. CH2 6, you don't have to. NH continues with C double bond O, so we formed our amide linkage. C double bond O, OH, and I put this outside. So if you have N molecules of this monomer and N of this, you're going to form N of this plus 2N minus 1 H2O. So these functional groups does not need to be shown up anymore because we are showing one segment. Now this, the commercial name for this is nylon. This is nylon, and since you have 6 carbon and 6 carbon here, this is known as nylon 6,6. You can change the number of carbons, and also you will change property of the polymer that you are going to produce.